So now that we have the logarithm as a new function, we want to be able to find its derivative. So if we start with, I'm just going to call it f of x is ln of x. We could just use the function notation for ln of x instead of f, but I'm going to use f anyways. If we try to find the derivative of this function using the limit definition, it doesn't work quite as well as it did for e to the x. So remember, if we start with this, we have the limit as delta x goes to 0. We have f of x plus delta x, but f is just natural logarithm, minus the natural logarithm of x all over delta x. And unfortunately, unlike the exponential, we cannot break up the natural logarithm of a sum. We could maybe use some properties of logarithms to, say, combine these two. We have a difference of two logarithms. We can turn that into a quotient. That's one of our properties. So we could write this as we have the delta x on the bottom, and then a natural logarithm of the quotient. But this limit is still not really something we know how to deal with. So what can we do here? It turns out there's a much simpler way to approach this. Instead of trying to use the limit definition, we can actually use the fact that we know it has a connection to the exponential function in order to help us. Remember, y equals the natural logarithm of x is exactly equivalent to x equaling e to the y. So what we can do here is differentiate this formula here using what we remember implicit differentiation. We used this back a couple chapters ago, where we had an equation that involved x and y, but it was not solved for y. But we were still able to get the derivative of y by differentiating both sides of the formula. So we're going to differentiate this formula and solve for the derivative of y. Remember, we do need to treat y as a function of x, and so we're going to have to use the chain rule for e to the y. Now, the x part is actually pretty simple. Derivative of x is just 1. But when we have the derivative of e to the y, we take the derivative of the outside function, so the e to something still becomes an e to the something. Remember, that's the derivative of our exponential function. But now we need to multiply by the derivative of the inside, multiply by y prime. This is actually pretty easy to solve. We just divide by e to the y, so y prime is 1 over e to the y. However, this is maybe not too satisfying because there's y's involved in the formula and not x's. We're starting with y equals ln of x. We'd like y prime to be some function of x. But remember, e to the y is x. That's exactly what it is. So really, y prime is 1 over x. That is our derivative. The derivative of the natural logarithm of x is just simply 1 over x. It's actually a lot simpler than what we started with, it seems. And it's actually quite important that we do have this derivative. But though we won't be seeing why it's so important until we start talking about the other part of calculus, the so-called integral calculus. Now we can also make a chain rule version of this formula. If instead of putting x into our natural logarithm, we put some function u of x. Remember, that means we follow this formula, but then we have to multiply by the derivative of the inside. So we have the 1 over u, but then we'll multiply by the derivative of u. So for any function, the derivative of that function over that function is actually just the derivative of the natural logarithm of that function. That fact actually even has some nice applications, though we're not really going to get into all that here. Instead, let's just work out some problems. Let's put these two new formulas to work. Start with problem 4. We have a function, f of x is equal to the natural logarithm of 8 minus x to the fourth. We want to differentiate this thing. That's all they're asking us to do. So when we take the derivative, we have the natural logarithm of something. All we need to do is put that something on the bottom, and then take the derivative of the inside, 8 minus x to the fourth. The 8 goes away when we differentiate. The minus x to the fourth becomes a negative 4x cubed. So we have the derivative of this stuff inside over this stuff inside. And that's all we need to do. It's actually not even any simplification we can do here. In problem 5, we again have the natural logarithm of something. This time there's actually the fourth root of 3x minus 5. This looks really complicated. When we have to differentiate, we'd say we put the fourth root of 3x minus 5 on the bottom. We'd have the derivative of that on the top, but then we'd have to use the chain rule for the fourth root and all that stuff. It turns out it's a lot easier to instead use properties of logarithms first. Remember, the fourth root is the 1/4 power. We can rewrite this formula as a natural logarithm of 3x minus 5 to the 1/4 power. And because we're dealing with a natural logarithm, one of our properties of logarithms says that any power that we have can actually be pulled out in front. So really, our function is 1/4 times the natural logarithm of 3x minus 5. That's actually a lot nicer already. When we have a factor out in front, that factor just comes along for the right. It's not anything complicated like a power that we have to actually differentiate. So when we take the derivative, we still have that 1/4 in front. The natural logarithm turns into a fraction, where we have the 3x minus 5 on the bottom, and then the derivative of 3x minus 5 is just 3. That's on top. And you could rewrite this in whatever fashion you want. Maybe distribute the 4 to the bottom if you prefer. But I'm just going to leave it like that. The point here is don't forget the laws of exponents, or the laws of exponents and logarithms. The laws using logarithm properties can actually simplify the things that you're trying to differentiate. Next, let's do problem 7. Here we have y is equal to the natural logarithm of x, but then to the 4th power. Note here that we're putting the 4th power outside of the natural logarithm. And that means that even though we do have a power, this is not something that we can simplify using the laws of exponent, or laws of, I keep saying exponent, the laws of logarithms. So we could simplify this if it's the natural logarithm of x to the 4th. This is just equal to 4 natural logarithm of x. But if the power of 4 is on the outside of the logarithm, we can't do that. These are not the same thing. So when we differentiate this thing, we're instead going to have to use the chain rule. So we have a 4th power as our outside function. Derivative of a 4th power is 4 times whatever's inside to the 3rd power, using that power rule. Of course, the inside is still natural logarithm of x. But now we also need to multiply by the derivative of the inside function. And remember, the derivative of the natural logarithm of x is just simply 1 over x. And again, we could rewrite this however you want to. I'm not going to change it. I'm just going to leave it as it is right now. Next up is problem 16. We have y equals a natural logarithm. Inside that natural logarithm, though, we have the square root of x plus 1 over x minus 1. Again, similar to what we had back here, we can actually simplify our function first in order to make this a lot easier on ourselves. If we were to try to differentiate it as it sits right now, we'd have to differentiate using the chain rule for the natural logarithm part, then another chain rule for the square root part, and then finally a quotient rule for the fraction that's inside. But because we have properties of logarithms, we don't have to do any of that. And say that y is equal to, because the square root is of 1/2 power, we can pull out that 1/2 power. And now the logarithm of a quotient is a difference. We have the difference between the natural logarithm of the top and the natural logarithm of the bottom. Of course, we do have to remember to distribute the 1/2 to both of those two terms, though. So we have the 1/2 of the natural logarithm of x plus 1 minus 1/2 of the logarithm of x minus 1. And now this particular form is a lot easier to differentiate. We take the x plus 1, put it on the bottom. We put the derivative of x plus 1 on the top. That's just a 1 in this case. We still have the 1/2. I'm going to go ahead and combine that into one fraction, though. Then we can do the same thing here, except instead of having x plus 1, I'm going to have an x minus 1. That doesn't actually change the derivative on top. So I'll have a 1 over 2 times x minus 1. It turns out that we can actually use this idea of being able to use properties of logarithms to our advantage in doing different derivatives of things that may not even involve logarithms. Let's say we had y equals the square root of x plus 1 over x minus 1, and we wanted to differentiate this thing. Now, we know we could use the chain rule for the square root and the quotient rule for this fraction inside, but that's a lot of steps. Is there a way we could simplify this? We could go ahead and take the natural logarithm of both sides. Essentially, turn this into an implicit differentiation problem. We've already seen how we can simplify this. We had that formula from the previous page. And then we've already differentiated this side. So if we differentiate both sides, remember this became a 1 over 2 times x plus 1 minus 1 over 2 times x minus 1. On this side, the derivative of the natural logarithm of y specifically, remember y here needs to be treated as a function of x. This is just going to be y prime over y, which means that the derivative of our original function, y prime, is equal to y times this difference. And in fact, we know what y is. That was our original function. This is just the square root of x plus 1 over x minus 1 times this difference. Now, this might not be exactly the same form that you would have gotten if you had used the quotient rule and the chain rule and all that from the beginning, but you can actually show that we do have the same result. And in cases where we have a lot of these factors, we have a lot of things multiplied, divided, lots of powers and stuff like that, being able to split it up into just a sum of these easy to compute derivatives can save you a lot of time. This is actually a technique called logarithmic differentiation. Now, we're not too concerned with doing that in this class. The book doesn't even mention it, but I like this technique so much that I did want to at least give it a shout out. But the point here is properties of logarithms are really a lot handier than people give them credit for. So we might as well take advantage of them whenever we can. We're also at a point where we can find the derivatives of exponentials and logarithms of different bases. So we've been using e to the x and the natural logarithm, which is base e. What about other bases? Well, let's start with the logarithm. We have the logarithm base a of x. This is actually equivalent to y. Well, if this is equal to y, this is equivalent to. Let me put the y in front. Y equals the natural logarithm base a of x is the same thing as x is a to the y power. But unfortunately, we don't know how to differentiate either one of these. We can't use the same trick as we did on the first page of this. But we had a law that we derived in the last section. We had what we call the change of base formula. That the logarithm base a of x is equal to the natural logarithm of x divided by the natural logarithm of a. And because we know the natural logarithm of a is just a constant, we're not letting a change here. It's just a particular number that we picked for the particular logarithm. It's a constant. When we differentiate this function here, we just have a constant times, so this 1 over a natural logarithm of a times the natural logarithm. And if we can differentiate the natural logarithm, we can differentiate this multiple of it. That means the derivative of this function here, of the logarithm base a, is equal to the derivative of the natural logarithm divided by the natural logarithm of a. Well, the derivative of the natural logarithm, of course, is 1 over x. And so I'm just going to put an ln of a down here on the bottom. So computing the derivative of any logarithm just gives us an additional factor of the natural logarithm of a. And do note that the natural logarithm of e is equal to 1. So if log base e gives us just the 1 over x that we expect. What about exponentials? We had y equals a to the x. Remember, we did try to differentiate this before. When we differentiated e to the x before, we noted that if we had a different number other than e, we got a to the x times some constant. Technically, this was a limit involving a to the delta x and all that kind of stuff. But we noted that we at least knew that it was some number times the natural, some number times a to the x itself. But we don't know what that number is yet. We want to be able to figure it out. The key about figuring that out comes from changing a to the x into a version of e to the x. Basically, if we take a to the x and we kind of introduce a canceling pair of the natural logarithm in e, then we can change this into something else. Basically, I'm going to take e to the power of the natural logarithm of a to the x. Remember, the e here and the natural logarithm cancel each other out, and we get the a to the x on the outside. But we're just kind of introducing them here in order to actually use properties of logarithms. Because the natural logarithm of a to the x, we can pull the power out. This is equal to e to the x times the natural logarithm of a power. This is actually a very important formula that is sometimes actually used to define what a to the x even means for irrational x's. So something like, what is 2 to the pi power? We talked about this before, where we had to kind of define it in terms of a limit, of basically putting in more and more digits of pi. Well, here we can actually turn this into e to the pi times the natural logarithm of 2. And if we start with some way to calculate e to any power, we can actually turn it into a way to compute any base, any positive base at least, to any power. And there's actually there's algorithms for finding e to any power. There's actually some very nice formulas for computing that. At least however many digits we need it to be. So sometimes this formula is actually taken as kind of a starting point for talking about exponential functions. Though we're kind of going a little off topic there. The point here, though, is that I can make use of this formula to differentiate this function. The derivative of a to the x is the same thing as the derivative of e to the x ln of a. And now I know how to differentiate e to some power. That power just has an extra factor of ln of a in it, though. So I use the chain rule. I'll take e to that power, and I'll multiply by the derivative. Well, derivative of constant times x is just that constant. And then I note that e to the x ln of a is just exactly what we had for a of x in the first place. So the derivative of any base to the x power is equal to that same base to the x power times the natural logarithm of a. This constant that we were talking about here, this limit that we had, actually is the natural logarithm of the base. Let's go ahead and do a couple problems that involve different bases. We're not going to do a lot with them. You'll find that in calculus, a lot of the times you just stick with e to the x and the natural logarithm, but it is important that we can actually deal with these. So in problem 39, we have a function h, which is equal to 4 to the 2x plus 3 power. We want to differentiate this thing. And when we take the derivative, remember we do have to use the chain rule here. So the derivative of 4 to some power, we're going to have 4 to whatever that power was, times the natural logarithm of 4, because we have to take the natural logarithm of our base. But now we also have to take the derivative of the inside. The 2x plus 3, we need to multiply by the derivative of that, which is just 2. So we have 4 to the 2x plus 3 times some constant, but there's really not a better way of writing that. That's just what it is. If we look at problem 41, we have y equals the log base 10 of x squared plus 6x. This is actually, log base 10 is something that we call the common logarithm. A lot of times when you see log without a base attached to it, that's what they mean, though you have to be a little bit careful about that. Some mathematicians, they think of the natural logarithm as being kind of the default logarithm so much that they just write log instead of ln. But if you write ln, everybody's going to know what you mean. If you write log base something, everybody's going to know what you mean. So writing log base 10 avoids any confusion. Alright, but we're wanting to differentiate this thing. And we're going to do it by just using our formulas. Remember, when we have a logarithm based something else, we're going to basically treat this as if we were dealing with an ln of this. So we're going to have this function on the bottom, and then the derivative of this function on the top. So the derivative of x squared plus 6x is a 2x plus 6. But because we're using a different base, we have to also divide by the natural logarithm of that base. And that's really the only contribution of the base to this formula. And there's no reason to distribute that ln of 10. It's just there. I want to go ahead and do one last problem. Just like we did with when we were dealing with e to the x, we had a problem where we actually graphed a function that involved e to the x. Here I'm going to go ahead and look at problem 72, where we had the natural logarithm of x, but then squared. And I want to know, well, what does this thing look like? How would I graph it? Remember that all this stuff is coming from chapter 3. We're going to go through each of those steps, looking for critical points, inflection points, all that kind of stuff, to try to find out what's going on with this function. First things first, what's our domain? Remember, the natural logarithm is kind of determining our domain here. The natural logarithm has a domain of 0 to infinity. We cannot put 0 and we cannot put negatives into the natural logarithm. Whatever result we get out, the square can deal with. So the square is not going to change that domain at all. So our domain is just going to be the same as the domain for the natural logarithm. From 0 to infinity. That means all of our number lines are going to start with a 0 over here. So we'll have y, we'll have y prime, I'll have y double prime. We'll go through all of those. But note, I'm not going to consider anything past 0. It's going to be my starting point for all of this. Let's start with just setting our function equal to 0. If I set this equal to 0, what could x possibly be? Well, note here that we don't have the square inside. It's on the outside. We've seen a situation like this before. In that previous problem, we had a 4 here instead of a 2, but we're going to handle it basically the same way. We differentiate the square first. We have a 2 times whatever is inside, but then times the derivative of the inside. The derivative of the inside is the derivative of the natural logarithm that's inside is 1 over x. And I'm getting way ahead of myself. I'm not taking the derivative yet. We'll come back to this. I'm sorry. We'll get to the derivative, and we'll go through all that again. Right now, we're dealing with setting this equal to 0 and solving. All right. So, what number squared can give us 0? Only 0 can. So, the only way this can equal 0 is if natural logarithm of x equals 0. What numbers can be put into the natural logarithm to give us 0? Note that we're not plugging 0 into the natural logarithm. There's no problem with solving this equation. In fact, this is not too hard to solve. If you remember, we can turn a logarithm equation into an exponential one. The inside here is now our outside. Our outside is now our inside of e to the whatever. E to the 0, well, anything to the 0th power, assuming we're not dealing with 0 down here. 0 to the 0th is a whole nother matter. But any non-zero number to the 0th power is equal to 1. So we do have 1 on our number line. Of course, we need to take some test points. I'm going to take 1/2 and 2. Remember, I need a number between 0 and 1, so I need to use some sort of fraction. And I'll just use the first integer after 1. So I have the natural logarithm of 1/2 squared and the natural logarithm of 2 squared. Now, one thing we can actually do if we want to use properties of logarithms is realize that 1/2 is 2 to the negative 1, and we can pull a negative out. In fact, we have a formula that natural logarithm of 1 over x is equal to negative the natural logarithm of x. So really, we could say this is the square of negative ln of 2. But the square gets rid of the negative anyways. So actually, these give us exactly the same value. But is that value positive or negative? Well, even if the natural logarithm of 2 were to be negative, the square gets rid of that. Both of these have to be positive just because of the square in the first place. They're actually going to be equal to 0.48 and so on. Not that that's too important to solve this problem. All right, what's next? Well, now we're going to talk about our derivative. So if y is equal to ln of x squared, and we've already started talking about this before, we're going to use our chain rule. We have the square on the outside, so we have 2 times the inside. But then we need to multiply by the derivative of the inside. We need to multiply by 1 over x, which we can even just go ahead and write this as 2 ln of x over x. But we're interested in where this thing equals 0. Well, a fraction equals 0 only if the top is equal to 0. The 2 doesn't really change anything. We're still looking at ln of x equals 0. And we've solved that already. ln of x equals 0 means that x equals 1. And so we can put on our number line a 1, and we take test points around 1. We get to basically use the 1/2 and the 2 that we had here and put them instead into our derivative. What is y prime of 1/2 and y prime of 2? This time we don't have the square to get rid of any negatives. So we'll have 2 times the natural logarithm of 1/2, which you could turn this into a negative 2 times the natural logarithm of 2. But we also divide that by 1/2. Let's just go ahead and use a calculator for this. We get a negative 2.77. For 2, we have 2 times the natural logarithm of 2 divided by 2. Well, the 2's actually can cancel each other out there. So what is the natural logarithm of 2? That's 0.69, and so on. I mean, I'm rounding here. I don't really need the full value of these. But the point here is that for 1/2, I have a negative. For 2, I have a positive. And we can tell right now that our function was decreasing from 0 to 1, and then increasing from 1 onwards. And that means at 1, it has to be a relative minimum, because that's a decrease down to it and then increase up from there. Finally, let's look at the second derivative. Of course, because we got a fraction in our first derivative, we are going to have to use the quotient rule. But it's a relatively tame one. I mean, we just have to deal with the fact that we have a natural logarithm on the top. So we take the derivative of the top. Well, 2 times the ln of x becomes a 2 times 1 over x. So our derivative of the top is 2 over x. We're going to multiply that 2 over x times the bottom. The bottom is just an x. Then we subtract the top times the derivative of the bottom. Well, the derivative of the bottom is a 1. So actually, I'm not even going to write it. And then we get to divide by x squared. And we can actually simplify this. 2 over x times x is just going to be 2. We have 2 minus 2 times the natural logarithm of x divided by x squared. We're going to set this thing equal to 0. Again, this is a fraction equaling 0, so the numerator has to equal 0. This time we don't just have natural logarithm of x equals 0. Instead, we're going to have to solve. But basically, that means that 2 equals 2 natural logarithm of x, or if we get rid of the 2, we just have that the natural logarithm of x is equal to 1. Again, we can turn this into an exponential equation. The x on the inside gets on the outside. The 1 on the outside becomes the new exponent, the inside. And of course, e to the first power is just e. And so that is going to be the one thing on our number line. I guess I could note here, and I should have noted this back on the first derivative, we can also ask where these don't exist. But, well, the fact of the matter is that since the natural logarithm restricts us to only talking about 0 to infinity in the first place, we don't have to worry about any zeros on the bottom. And the same thing here. We can't have 0 anyways, so it's not going to result in a critical point or an inflection point. We still need to take our test points, though. And we can go ahead and, because we know that e is about 2.7, we can can go ahead and take 1 for one of our test points. 1 is a pretty easy number to plug in here, because when we plug 1 into the natural logarithm, we just get 0. And then, of course, we just have 1 on the bottom. So we end up with a positive 2. Fortunately, we have to go all the way out to 3 for the other interval. So we have to go past 2.7. We plug 3 in here. Again, this is really pretty much just a calculator problem. Just go ahead and plug it in. I get negative 0.022 and so on. Specifically, we get a negative number. That's what we need to know. We had a positive here and a negative here. We can go ahead and graph this. Note that we don't really have to worry about negative x's, and in fact, we know that our function only gets down to 0 at 1. It never goes negative. So really, I'm just going to draw my axes at the extremes. We don't have to worry about anything in these other quadrants. We know let's mark off 1, 2, and 3. So we also have here E is maybe around here. Go ahead and plot our points. We know at 1 it does bottom out at 0. We also know that E is an important point on our graph. At E, what is our value of our function? Well, natural logarithm of E is equal to 1. And 1 squared is obviously 1 as well. So we can go ahead and say that that's 1 there. Maybe I'll even label them. We have an E, we get up to 1. We know that we have a local, keep wanting to say local because that's the term I'm more familiar with. I'm trying to stick with the book though. A relative minimum at 1. It bottoms out there. And it also does have an inflection point at E because we do change our concavity. So it is concave up. It has a cup shape here. It has to bottom out at 1. But then it becomes cap shape over here. So it gets more like that once we hit that point. So kind of just draw it in here as best as I can. So I want to have that curved upwards shape here. And then it has to actually start curving downward a little bit over here. Now, to actually finish our graph, we might want to know what's happening around 0. Does it approach a limit? Is there a point on our y-axis that it approaches or not? How should we know? Well, we can look at limits. What is the limit of the natural logarithm of x squared as x goes to 0? Specifically from the positive side. We can't talk about the negative side. Well, what is the natural logarithm doing? The natural logarithm is going to negative infinity. Remember? If we square negative infinity, numbers that are going to negative infinity are instead going to go to positive infinity. So really, this is actually going to positive infinity. So rather than actually approaching a number, we actually have an asymptote here. It is going to be approaching the y-axis as x goes to 0. You might be wondering, maybe there's a horizontal asymptote. Does this level off somewhere? Well, there we're actually talking about what is the limit as x goes to infinity of the natural logarithm of x squared. And again, we have to think about what is natural logarithm doing as x goes to infinity. The natural logarithm is going off to infinity. And of course, squaring something that's going off to infinity is just going to result in even more infinity. So actually, this never does stop increasing. It increases off to infinity, even though it is slowing down as it goes because it is concave down. So this might not approach infinity very fast, but it does approach infinity. We can go ahead and actually take a look at this in Geogebra too. So our function is y equals the natural logarithm of x squared, and we get this shape here. Of course, the graph that we drew is actually a lot more zoomed in here than what we have here. We could zoom in so that, yeah. So from 0 to 3 and from 0 to 2, we get this shape here. Of course, we bottom out at 1, 0, and then we also have the point at e, comma 1. So maybe it's a little harder to see that we do have an inflection point there, that it was concave up here and it's now concave down there. It's a little bit more subtle when you actually look at it. But though you can tell when you zoom out more that it does slow down its increase as we go. And we do have this vertical asymptote at 0. All right. But the point here is we have a way to differentiate the natural logarithm. And we can use that derivative in order to do a lot of stuff. We have one last section from this chapter. We'll be talking about next time, and it'll be the last lecture before our exam. We'll be talking about applying the exponential function to various applications. So I'll see you there.